Hi everyone, my name is Max, and today I'm going to explain to you what mathematical induction is. Now, before we talk about what mathematical induction is, let's establish our domain. First of all, math induction is a proof method that we're going to use for a proposition that works for all natural numbers. Now, what does the mathematical induction look like? Well, it reminds you of a domino. You know, if it's true for one number, it's going to be true for the next one. If it's true for that one, it's going to be true for the one after the next one, and etc. It keeps going. It's like a chain reaction. But if we have to prove that some statement is true for every natural number, then how many steps do we need to prove it? Well, the first answer that comes to mind is infinity. What I mean by that is that we check that the statement is true for every single natural number, and we do one step per number. But there's actually a more simple method of doing that. We can prove that a statement is true for any natural number in only 3 steps. And this 3-step method is the mathematical induction that we're going to be talking about. Now, let's look at the steps. The first step is the base case. The base case is when we prove that the statement P is true for the natural number 1. The next step is the induction hypothesis. What we do in this one is assume that the statement P for the natural number K is true. And the third step is the induction itself. And in this one, we need to prove that if the statement is true for the number K, then it's going to be true for the number K plus 1. Now, if we did that and we apply the same logic to if we assume that it's true for K plus 1, then we know it's true for K plus 2. And then it goes on for K plus 3, K plus 4, and again, it's the domino effect like I explained. Now, to practice using this method, let's look at an example, a theorem that we can prove via mathematical induction. Now, this theorem states that n squared equals the sum of all odd numbers up until 2n minus 1. Now, just in case I'm going to visualize this theorem, let's say we have a square 3 by 3. As you can see, inside of the whole square, there's going to be 9 of these smaller squares. But if we look at these L shapes, the dark blue block at the top left, the L shape in the middle, the green one, and the one in the bottom right, the light blue one, then we can see that this theorem works in visual terms. But we still need to prove it mathematically. So let's do that. Now, in our case, the statement is that n squared equals the sum of all odd numbers up until 2n minus 1. Now, let's look at the base case. The base case, like in the square I showed you, says that 1 squared equals 1, and it's true. So we've already proven the base case. Now, let's look at the induction hypothesis. 1 plus etc. plus 2k minus 1 equals k squared. Now, if it's true, then let's prove that it works for k plus 1. Now, the next odd number after 2k minus 1 is going to be 2 times k plus 1 minus 1, which equals 2k plus 1. We're going to prove it in a minute and rewrite it, don't worry. So, what this means is that this sum is going to be bigger than the last sum by this number that's written 2 times k plus 1 minus 1. But again, it's written in a complicated form, so let's rewrite it. The previous sum equals k squared. Let's establish that because we assumed that it's true in the induction hypothesis. So now that we've done it, I'm going to tell you why 2 times k plus 1 minus 1 equals 2k plus 1. Now, 2 times k plus 1 minus 1 equals 2k plus 2 minus 1. And 2 minus 1 equals 1. So that's why the difference between these sums equals 2k plus 1. Now, what does that mean? This means that the entire sum equals k squared plus 2k plus 1. And what does this formula remind you of? To me, it looks like the next square. Now, if you want to verify it, you can use the formula that a plus b squared equals a squared plus 2 times a times b plus b squared, where you can say that a equals k and b equals 1. So there you go. We've proven that it works for k plus 1. So we've proven the last third step. And this means that we've proven the whole theorem with mathematical induction. And what does this mean? This means that we've proven a statement that works for every natural number in only 3 steps. Isn't it cool how you can just do that? Now, I hope after this video you know how mathematical induction works. And thank you for watching this video.